Good morning, everyone, and thanks for coming along. Welcome to the people online as well as in the room today. So before we get started, we'll just do a little bit of housekeeping. If there's an emergency, just follow everyone out onto the grass over there. If you need a bathroom, they're just under the stairs, just as you kind of exit this building room. Yeah, I think that's about it for housekeeping, really. So without further ado, we are hearing from Emily today. She is in her final year of her PhD here at RIEL at CDU. Before she came here, she was in Western Australia researching eagle rays. And so if you don't know much about Emily, she likes fish. And she is also looking for cheese recommendations this year. So, yeah, there you go, Emily.
Thank you. Thank you all for joining me on your Friday morning. For those of you who don't know me, my name is Emily. Like Christina said, I am a final year PhD candidate at Charles Darwin University. And today I'm going to be discussing if sensory deterrents can reduce shark and ray bycatch in Australian gillnet fisheries. I'd like to start by acknowledging all First Nations people across the lands of which we work and live. And I'd like to pay my respects to elders past, present and emerging, and extend that to any First Nation people in the room or online. So just a brief overview before we get into it. We're going to start with a bit of a background into the work before moving on to the two main components. So we did a captive aquarium trials where we tested 2 deterrent devices in an aquarium setting, and our field trials where we tested the same devices but in a larger scale fishing operation. So let's start with a couple of definitions so that we're all on the same page. So target species are the species that are targeted or intentionally sought after in a fishery. Byproducts are non-target species that are still able to be retained. Discards may include threatened species or other undesirable species that are unable to be retained either due to legal constraints or just undesirable. And bycatch represents any non-target species. So this can include discards and byproducts. Our TEPs represent any threatened, endangered and protected species. They are considered threatened under the IUCN listing or protected under the EPBC Act. Species of conservation concerns include species that are not considered TEPs but are threatened globally. And the shot is the deployment and the receival of one net. So you can have multiple shots in a day of fishing. So fishing is a critical component of global food security. It provides a source of nutrition and protein to billions of people worldwide. In Australia, our commercial fisheries are well managed with strong regulations, monitoring and stock assessments to promote sustainable harvesting. Fishers play a key role in the sustainable fisheries, actively complying with regulations, adapting practices and contributing to data collection and monitoring programs. Despite this, however, fisheries do face challenges through direct and indirect impacts. So direct impacts include overfishing, bycatch, or the injury or death of threatened species, and indirect impacts can include habitat destruction, pollution, and ghost fishing. These impacts not only influence fish and threatened species populations, but also disrupt the ecological balance. So effective management is required to ensure the viability of future global fish stocks. Luckily, technological advances have proven useful to mitigate interactions with gear. So mitigation methods, such as deterrent devices, are being developed to reduce the bycatch of threatened species and limit their interaction with commercial fishing gear. So many elasmobranchs, also known as sharks and rays, are typically upper-level predators, which are able to manage population of smaller predators and herbivores. Not only this, but due to long-distance migrations, elasmobranchs assist in transporting nutrients between linking ecosystems between different oceans. Some elasmobranchs are considered keystone species based on their ability to modify habitats. And they also hold socioeconomic importance. So ecotourism is based on viewing or interacting with marine megafauna, such as through diving or fishing. This provides money to coastal areas and helps people learn more about these animals. Many Indigenous communities also have cultural ties to elasmobranchs, incorporating them into traditional practices, stories, and hunts. Research into elasmobranchs is also important to the scientific community, providing an insight to the biology, behaviour and ecology of various animals and future informing fisheries management. So commercial fisheries often interact with various species, including target and bycatch species. Of these, they can include elasmobranchs. So elasmobranchs are often susceptible to fishing pressures due to their external teeth, fins or spines, or other morphological traits. Due to having a K-selective life history, such as slow growth rates, late maturity, or low reproductive rates, increased mortality can be detrimental to the population size. This also extends to threatened species and species of conservation concern. Elasmobranch bycatch rates are common in fisheries globally. However, in Australia, they are high in net-based fisheries. So I've mentioned a lot about bycatch and threatened species. So what are these species that are commonly caught? It is important to note that in Australia, some fisheries are able to retain sharks. So not all shark species are inherently considered bycatch. So common bycatch includes spot-tail sharks and other whaler sharks, which are also able to be retained as byproducts. Less milk sharks, hard-nosed and sharp-nosed sharks are also considered byproducts. And less commonly caught species such as zebra sharks and eagle rays are often discarded. Our threatened elasmobranchs include our devil and manta rays, as well as 4 species of sawfish, including our dwarf, large tooth, narrow and green, and as well as 2 species of river sharks. Our other threatened species include marine mammals such as dolphins, marine reptiles, and sea snakes. So one type of fishing pressure in Northern Australia are gillnets. Gillnets and pelagic are also considered pelagic nets, consist of a sheet of thin twine framed by a rope with floats and a weighted lead line. They're held in the water column through floats, and it is considered a passive method where fish get caught either by swimming through the net and getting stuck on the gills, spines, teeth, or fins. It can be selective based on the mesh size, so a larger mesh size will allow smaller fish to swim through. However, the selectivity is low, with high levels of large-bodied bycatch still being observed. So as the interest of threatened species and elasmobranchs do increase, various practices have been developed to reduce the interaction rates with commercial fishing gear. These include time area closures, no fish zones, and modifying gear to reduce bycatch interactions. Successful mitigation strategies have been identified as those that prevent or minimize the bycatch of threatened species without influencing the target catch, those that are practical and affordable to implement, those that have demonstrated efficacy through fishery-dependent testings, and that do not jeopardize the safety of the crew. So to reduce the interaction rates in fisheries globally, deterrent devices have been tested. Now, these deterrent devices exploit the senses of an animal. There are 5 main types. So the acoustic deterrents are commonly used to target the auditory system of an animal. These predominantly target echolocating marine mammals due to their sensitivity to sound. Olfactory deterrents target a species' sense of smell, and these are typically used on longline fisheries or bait and hook fisheries. Tactile deterrents include barriers, however, this is still uncommon. The visual deterrents can include a change in gear color, bait color, or the addition of light, and this increases the visibility of the gear. Electric deterrents exploit the electroreceptors of an animal, predominantly elasmobranchs, due to their sensitive specialized receptors known as the ampullae of Lorenzini. So lights have showed promise in reducing turtle, seabird, and cetacean bycatch in Peruvian gillnets, as well as elasmobranchs and Mexican gillnets. They've also showed deterrence of captured benthic elasmobranchs, including Port Jackson sharks and epaulet sharks. However, there are mixed results noted of elasmobranch deterrence in Peruvian gillnets. Pulsed electric devices have shown a success in elasmobranchs, including captured sandbar shark, sand tiger sharks, and sawfish, as well as field trials involving blue sharks and pelagic stingrays, and depredation studies of the bonnethead sharks. The variability of deterrents highlights the species and context diversity of the deterrents. We worked with industry to shortlist different deterrent devices based on the information above, and as they're the greatest interest to the industry. So in order to reduce the interaction rates of elasmobranch bycatch in Northern Australia, we aim to test off-the-shelf bycatch deterrent devices. This means that anyone can go out and buy these gear and implement them onto their fishing gear. Making them off the shelf will also help with the uptake of the devices if proven successful. We aim to test these devices for target and bycatch species, specifically looking at elasmobranchs. So I have some prompts. We use the FishTech Marine Net Light, which is a static green LED designed for net fisheries. The net light is waterproof and depth rated to 1200 meters with a battery life of 500 hours. Please feel free to pass. We also use the FishTech Marine Shark Guard, which is initially designed for longline fisheries. It is a pulse electric deterrent that emits a 30-volt pulse for 1.5 milliseconds every 2 seconds. Supplied with a 3.6-volt lithium battery, it has a battery life of 65 hours, and based on the electric threshold of the pelagic stingray, its effective range is about 12.5 meters. Both devices are active upon contact with the water and are accessible for fishers. Before each trial, the net light was tested underwater to ensure functionality, while the Shark Guard was tested using the Picoscope 7 software available through FishTech Marine. So we now have the devices. What are we going to do with them? So we wanted to comprehensively determine the efficacy of both devices. We did this through doing an aquarium trials, which we monitored fine scale behavior reactions to these devices before we scaled up to our fishery dependent trials to examine the catch rates at a larger fishing condition. So our aquarium trials were set in Moreton Bay. We caught 5 giant shovel-nosed rays in an active commercial tunnel net fishery, while 3 brown-banded bamboo sharks were caught on hook and line. Individuals were then transported to the Moreton Bay research station in the Blue Dot to be held in a 10,000-litre tank and fed until station daily. So sharks and rays have different sensory ecologies, so we conducted trials with different species to assess these different reactions. Trials were held in a 2,800-litre tank. An experimental net was constructed using longitudinal strands of monofilament placed across a 1-metre PVC pipe spaced at 9-centimetre intervals. This was to mimic commercial gear operations. No latitudinal strands were provided to limit the risk of entanglement to the animal and to limit the stress. Each animal was given 15 minutes to acclimatise before starting the trials. Giant shovel-nosed rays were held in the tank for 10 minutes with every interaction documented, while the brown-banded bamboo sharks were only exposed to each trial for the first interactions. This was due to the bamboo sharks having a lower activity. Each individual was given 24 hours between trials to limit the stress and familiarity with the net, and during the trials, an overhead camera recorded all interactions. All 5 giant shovel-nosed rays and 2 of the 3 brown-banded bamboo sharks underwent 6 trials, so 2 trials per treatment, our control, light and electric, while the remaining brown-banded bamboo shark only underwent 1 trial per treatment. So we did note a couple of behaviours. Interactions included being deterred and not deterred. We considered becoming in contact with the net to be not deterred, as in a real commercial setting, this would result in capture. The majority of animals were not deterred by the device. However, we did see that the shovel-nosed rays were more likely to be deterred in the light treatment. We did also note that the giant shovel-nosed rays did become side on with the net quite a few times, which may show awareness to the light. So the probability of deterrence was significantly higher in the light deterrent in comparison to that of the control. However, as noted in the bottom graph, this did decrease over time. And during that 10-minute trial, we didn't note any difference in deterrence. For the brown-banded bamboo shark, there was no difference in deterrence between treatments. So as I mentioned earlier, giant shovel-nosed rays and bamboo sharks have different sensory ecologies. Shovelnose rays have dorsolaterally positioned eyes with an enhanced spatial awareness. Bamboo sharks, however, are more visually restricted and have ventrally positioned, less mobile eyes to rely on contrast rather than on colour. Both species have ampullae pores concentrated to the ventral head and rostrum. In this study, the pulse electric device was affixed mid-depth to cover a greater area. However, if moving the device lower, closer to those ampullae pores, may show a different behaviour. Prior laboratory studies noting deterrents typically have higher voltages and or frequencies. So it's likely that the low frequency and low voltage output of the shark guard may be insufficient to elicit an aversive response. There are, of course, limitations to this study. There was a low sample size with only 5 giant shovelnose rays and 3 rounded bamboo sharks that would not typically be found in these commercial operations. We also conducted this trial in a small artificial tank, which, with the stress of the aquarium environment, likely not representing that of the field. However, the experimental trials did allow us to look at these fine scale behaviours and see how they would react to different devices. So we then conducted our field trials. We did this using a multi-fishery approach, working both within the Northern Territory offshore net and line fishery and the Gulf of Carpentaria inshore fin fish fishery. Both fisheries target mackerel and blacktip sharks and are able to retain whaler sharks and finfish as byproducts. Typical discards of both fisheries include milk, hardnose and sharpnose sharks, as well as eagle rays. Species of conservation concern include 3 species of hammerhead sharks, which are considered no-take in Queensland and quota managed in the Northern Territory. And interactions with certain species are infrequent. These fisheries are important as they are some of the last remaining pelagic gillnet fisheries in Australia and are relatively small in operation compared to the large size that they go in. In comparison to neighbouring developing countries, Australian fisheries are well managed with interactions with threatened species, species of conservation concern, and all retained species being required to be recorded. Due to some slight operational differences, the study design was altered to fit the specific context. So in the offshore net and line fishery, we used a 990 metre net comprised of a mix of green twine and monofilament of varying sizes. In the Gulf of Carpentaria, we used a 1800 metre net comprised entirely of monofilament. In both fisheries, the devices, which I have here, were attached to the float line and one between each float, between the float and on the float, causing the devices to be attached at 7.5 metres apart in the offshore net and line and 12.5 metres apart in the Gulf of Carpentaria. The devices were attached with relative ease with some entanglement issues during the whole, which we'll touch on a bit later. So we conducted these trials in March and June to July for their respective fisheries, and all fishing occurred after sunset. There were up to 3 shots per night, dependent on the fisheries, and all nets were set between 2 to 4 hours. All animals were identified to the lowest taxonomic level, with the distance to the device and any level of depredation being recorded. In the offshore net and line fishery, we got 19 shots. However, one replicate of the electric device and its control counterpart did have to be removed due to intense entanglement of the net. In the Gulf of Carpentaria, we had 27 shots. In both fisheries, the target species, so the mackerel and blacktip sharks, dominated the catch with limited threatened species interactions. There was also high variability noted between the sets. So unfortunately, we didn't catch as many threatened species as we would have liked. Not that you want to catch any, but in the offshore net and line fishery, we caught 1 longhorn pygmy devil ray in the electric section of the net. For the Gulf of Carpentaria, we caught 1 narrow sawfish in the control sections of both treatments, as well as an additional 2 in the electric section of the net. We did also catch 1 sea snake in the electric section of the net in the Gulf. While we couldn't do statistical analyses of threatened species, we were able to look at hammerhead sharks and the target catch. So, there's a couple of graphs coming up. I'll recap them at the end. For the light treatment, there was no impact on grey mackerel. There was a significant decrease in the catch rates of blacktip sharks in the twine section of the net. However, the light deterrent did not influence this. There was a significant decrease in the light section of the twine net of spot-tail sharks and a moderate increase in the light section of the twine part of the net for aggregated hammerhead sharks. In the Gulf of Carpentaria, there was no influence on any threatened species, on any target species or spot-tail sharks. There was a significant decrease in the light section of the commonly discarded milk shark. There was no influence on aggregated hammerhead sharks. However, all great hammerhead sharks were found exclusively in the light section of the net. However, there is only a sample size of 7, so more power is needed to determine these trends. For the electric device in the offshore net and line fishery, there was no influence on either target species. There was a significant increase in the electric section of the monofilament net for the spot-tail sharks, and a moderate decrease in the electric section of the twine net for aggregated hammerhead sharks. In the offshore net and line fishery, there was no influence of the treatment on any species. So to recap that, for the light, there was no impact on target species in either fisheries. There was a significant reduction of spot-tail sharks in the offshore net and line, and a significant reduction of milk sharks in the Gulf of Carpentaria. There was a moderate negative effect on aggregated hammerhead sharks, with all great hammerhead sharks being found exclusively in the light in the Gulf of Carpentaria. For our electric device, there was no impact on target species again, and there was a significant increase of spot-tail sharks in the offshore net and line. There was a moderate positive effect on aggregated hammerheads in the offshore net and line as well. So depredation remained consistent between the two deterrents and their respective controls for both mackerel and elasmobranchs. The location of catchment for black-tip sharks and hammerhead sharks were not influenced by either device. However, the location of grey mackerel was influenced by both devices. Using a linear model, the occurrence of grey mackerel was significantly higher closer to the light. There has been noted in other mackerel species to be a halo effect, where being closer to a light means that they're more likely to school, whereas further away from the light, they're more likely to be solitary. Meanwhile, using a polynomial model, there was a marginally lower catch rate of grey mackerels closer to the electric deterrent, with higher catch rates noted at approximately 5 metres before dropping. So we know how this impacts the animals, but what about the operational feasibility? So both deterrents were attached and removed with relative ease. However, there was some entanglement issues during the whole of the electric deterrent. However, this may be likely due to the monofilament attachment. As you can see, it's very kinked and it gets very tangled. We did lose a couple of both devices. However, this can be rectified with an elastic band around the light deterrent and a small clip at the end of the shark deterrent to avoid losing these. With the battery life, there was some attraction of smaller invertebrates to the casing of the light deterrents, predominantly small prawns. Using 2 AA batteries, the light deterrent has a battery life of about 500 hours, while using a 3.6-volt lithium battery, the electric deterrent has a battery life of about 65 hours. In terms of accessibility, the light deterrents are readily available from the website, with some devices being out in the field at the moment, while the electric deterrents are still in the trialling phase and are not ready for commercial selling. In terms of price, there is a bit of a difference, with the light deterrents priced at approximately $25 each, while the electric deterrents are about $200 each. So again, the deterrence of some species but not others likely reflects a difference in sensory ecologies. As I'm sure many of you are aware, in Northern Australia we have high turbidity, meaning the water is a bit cloudier. And this could limit the range of the light deterrent. The shark guard was also originally designed for a longline fisheries where capture occurs at a singular predictable point rather than an entire net face. Similar to that of the aquarium trials, the electrical parameters of the electric deterrent may be too low to elicit any major aversive responses. Again, there are limitations. There was high variability between the sets, likely reducing statistical power. There were also minimal interactions with threatened species, so we were unable to conduct any statistical analyses. Fishing in both fisheries was also conducted under a full moon period. This time has been noted to have lower teleost activity. So we've done all that. What's next? If you'd asked me 5 months ago what the next steps would be, I would say Nothing. I have a PhD to finish. Don't talk to me. However, an opportunity arose where one of the fishing operators wanted to continue the trialling of the LED deterrents on their vessels. So using onboard camera systems, electronic monitoring is used to validate commercial fishing logbooks. This also happens to be another one of my PhD chapters. However, we can use the footage to identify species in each section of the net and conduct the experiment from land over 3 boats over a longer period of time. So lights were attached to floats of a net of up to 1,800 metres, spaced at 25-metre intervals. There are 2 treatment sections, both light, and 2 control sections. Fishing occurred in both the Gulf of Carpentaria and in the offshore net and line fishery. So from August 2025 onwards, lights have been added to 3 vessels that operate within this area, with a couple of hundred shots being able to be reviewed. So we've gone from 27 shots up to a couple of hundred. There are up to 2 shots per night, with the nets also being set for about 2 to 4 hours. All animals are again identified to the lowest taxonomic level, with any level of depredation being reported. And data from this will allow us to clarify trends, specifically for hammerhead sharks, and identify any trends for threatened species. It will also help us clarify trends and operational feasibility for an extended period of time. So, kind of wrap that up. So we aim to test off-the-shelf bycatch deterrent devices. We did this using 2 different methods, our aquarium trials and our fishery-dependent trials. We found that in the aquarium trials, giant shovel-nosed rays were more likely to be deterred in the light deterrent. However, this did decrease over time. While in the fishery-dependent trials, we found that there was a potential attraction of lights by hammerhead sharks in both fisheries, and the potential decrease in hammerhead sharks in the electric deterrent. And what's next is that we're conducting further trials, hopefully increasing that sample size and getting a couple of trends. So in terms of future work, we recommend doing further trials. That's every scientist's next step, is do more trials. Further laboratory trials with more relevant species are recommended. So we did use giant shovel-nosed rays and brown-banded bamboo sharks, which are unlikely to interact with these fisheries. So using whaler sharks or other species that are likely to interact is recommended. It's also recommended to trial different electrical parameters to determine the sweet spot and to elicit aversive responses. We also recommend trialing different positionings of the net to gain the most deterrence. So there was high variance between species and fisheries, highlighting the species and context specificity of both devices. Both the devices are operationally sound. However, they did not show enough of a deterrent effect on bycatch species to warrant industry implementation. So currently they're not recommended. However, we are conducting those further trials, so this may change. So this is very much a stay tuned space. I would like to thank the funders for this project. These trials were conducted under the Threatened and Migratory Species Fisheries Bycatch Mitigation Program from DQ and co-funded by the FRDC, with in-kind support from Charles Darwin University, Northern Territory Department of Agriculture and Fisheries, Western Australian Department of Industries and Regional Development, and AusTop Fisheries. I'd also like to thank our industry partner, Ren Fishing Group, who are continuing these trials of the devices, as well as for the support from the Northern Territory Seafood Council. I'd also like to thank my Northern Shark and Ray Research Group for supporting me through this, my friends and family, and you guys for all coming. Are there any questions? If not, please enjoy some videos of my shovel-nosed rays eating. Hopefully that will stop you from asking questions.
Just excuse me, before questions, we're just going to change the audio settings because currently it's all coming through this mic.
They're not very good at eating now.
They get that. They get that.
Is it because they did?
Pretty. You're not allowed to release my prey.
Right.
Any questions? And the this microphone is this green light on the ceiling. So you're aware with it.
In your longer trial, so my understanding of the results was that you got an increase in hammerhead sharks, which is not good, but also potentially an increase in mackerel.
No influence on mackerel.
So no increase in the actual amount of mackerel that you catch, but they tend to be closer to the light. Right? Would it be worth in your longer trial to do some back of the envelope economic analysis about the effect of either the increase in bycatch or decrease, to look at whether it's actually economically quite helpful as well?
There's definitely something to look at. My background isn't in economics, so I would probably have to ask other people for help with that. But yeah, it is something to look at to see if it is viable. But yeah, we did just find that there was no change in the catch rates of either mackerel or black tip sharks. So it's more of a deterring the bycatch.
If the mackerel is schooling around the lights, why aren't they being caught?
I don't know, to be honest with you. I'm not sure why there wasn't a decrease. If we did find it, it's just over the period. There could be a decrease later in the net, and it all evens out eventually.
So it was really interesting for someone who doesn't work on fish, me. And I'm sorry if I missed this at the beginning, but what kind of claims do the people who actually sell these devices make about their efficacy?
Yes, so there are quite a few studies that have looked at both the lights and electric and pulsed electric deterrents. So we mainly did, we based this around the study that looked at the blue sharks and pelagic stingrays for the electric deterrents. And we looked at the Mexican gillnet elasmobranch deterrents there, but they have been proven useful for other megafauna, so like the marine mammals and turtles and stuff. Did that answer your question?
Okay, makes sense.
Thanks, Anne. That was really great and seems like a really worthwhile study as well. In particular, I'm curious about the fact that I think one of the best outcomes of what you've done is that the fisheries want to continue testing devices. I think that's fantastic. And I'm really curious in regards to, I know you said a control trial, and that's a good way of doing it. Did you get any anecdotal input from the fishery staff themselves to say whether they, on your trial nights, they noticed a deficit? You're testing deterrents.
Yeah.
So interestingly, you're looking at the species you caught, not the species you didn't catch.
Yeah.
So for the people doing those fishery jobs every night, they would be able to say, oh, we actually normally get turtles, seabirds, stingrays, but the nights you did it, we didn't. Was there any of that kind of?
We didn't really have that kind of discussion. There were a couple of shots where we didn't catch anything. And so I know, like a bit of last season, the fishing effort wasn't as great as it normally would be. So we didn't have those conversations with the crew, but it's definitely something we can ask them with the longer trials if they've noticed anything over a longer period of time.
That's really good. I might have missed it, but when you're placing the devices, what's their kind of like recommended placement? I was just thinking about the one being $25 and one being $200. Do they have the same? Like, do you need the same number of them?
There wasn't a range noted for. There wasn't a range noted for the net light, but for the electric deterrent, its effective range is about 12.5 meters. So that distance in the Gulf of Carpenter area where we had that longer distance apart, it theoretically should have covered that part of the net. But for the lights, we didn't get a value.
I imagine, just to follow on from Jenny's question, I imagine that in the time that a PhD happens, that the technology must move on. And I wonder whether the manufacturers know about the results, have commented on them, and have a new answer in what they're releasing now?
Yeah, I'm not too sure, to be honest with you. And there are a couple of, like, especially because like these electric devices are designed for the longline fisheries. So there is results where it has worked very well for there, whereas in here we have used the gillnet space and it hasn't worked quite as well. So it is like potentially another product when they get the results that they can be, oh, we can make this a bigger range.
So you do have that connection with them, so that they do have the results.
We have a connection.
That's what you need.
What you've shown here is that, you know, you've used some very generalised devices for a range of species that all have different sensory sort of capabilities, etc. So to me, it sort of says that there might be a capacity for tweaking specific design, given, you know, the capabilities of different animals. So what do you recommend? Not what are you going to do, but you're nearly done.
I think that, especially with the electric deterrents, I think that having a different frequency and voltage and trialing the different ways that you can do that would result in something. Not sure if it's what we need, but it would result in something. And I think with the light, our water a little bit more is needed as well. Hannah.
Northern Australia.
There could be an option for Northern Australia. Our focus is mainly on the elasmobranchs, and so the elasmobranchs don't require sound as much, whereas those echolocating marine mammals, so dolphins, for example, it would work a lot better for them than it would for elasmobranchs.
Oh, sorry. You mentioned trialing some on different parts of the net. Do you have any info about where in the net the most bycatch occurs?
On our field trials, we did look at, we did determine if they were found in the top, middle, or bottom of the net. Haven't looked at that yet.
Other questions?
Otherwise, we can give Emily another round of applause. Thanks, Emily. In a couple of weeks' time, we have our next seminar series, which is on crocodile carcasses, which is kind of like fish in a way. So all your fish people, fish people definitely want to come along to this one as well, surely. No, that's maybe the wrong audience for our next talk. No. And actually, and everyone here is invited to morning tea which will be ready in like 15 minutes or so. So you just follow everyone else from here into kind of another building to get to it. But thank you all for coming.